So now we know the basic procedure how to calculate the eigenvalue and the eigenvector. In real-world application, probably you won't get so small, so easy one. But we have the tool. I have all the commands for you. All you need is use the MATLAB to run those commands to find the solution. One thing I wanted to point out, this little sim means we are going to do symbolic calculation. The result you find, you have those square root. It's accurate, but symbolic. If you don't want the symbolic calculation, what you can do is put either a numerical value. What is that, a numerical value? Oh, this is the magic. VPA, that's the command to make it as a numerical answer. It's also ugly, but if you round off a little bit, it looks better. I will let you to read the instruction, especially the help menu, but it's good first to run those and use the MATLAB to check your answers. Our third example, we will look at the eigenvectors of a 3×3 matrix. There's no difference except the complexity of the calculation. But I'm not going to go through too many of those calculations. First, you write this characteristic equation. See, in the major diagonal, we're going to subtract the r, what we used to call denominator. You can call any name. And the matrix we are looking for is this A. You see the major diagonal is 1, 1, 1, and all the rest, they have a nice symmetry. If you change the rows into columns, you get exactly the same. We call this kind of a matrix as symmetric matrix. If you swap the row and the column, you see the 1, -2, 2, and the 1, -2, 2, they're the same. Or in another word, it's symmetric with respect to the major diagonal. So it's a symmetric matrix. So when we try to solve this, we're going to get a cubical equation. The highest power is 3 because you have r times r times r, you get the r cubed. If the matrix have an n by n dimensional, then you are going to get the r to the n. The polynomial will be n degree. In the previous two examples, when n equal 2, we got a quadratic. Sometimes you're going to have difficult to solve the cubic equation. Fine, use the MATLAB. There's a command called solve. It's going to finish the job for you. Anyway, we solved this equation by substitution here. We found the 3 solutions. But the -1 is a repeating solution. See, we got the -1 twice. So we got a single solution and a repeating solution. In other words, I really only get 2 eigenvalues. Because this is 3×3 matrix, I still hope I can get 3 eigenvectors. So let's see how we got all the vectors. Start from the easy one. When the r equal 5, it's a single solution, and we assume the v is going to be u1, u2, u3, and replace this r by -5 by 5. Put the 5 here in the major diagonal. You got the -4, -4, -4 on the diagonal. So this matrix is our A minus lambda I times V1. And then equals 0. Or again, we understand this have to be singular. How do I convince you it's singular? Look, if I add the first row and the second row all to the third row, what do you have? If I add, let me think this way. Oh, this way. Let me add the first row to the third row. What you get? Negative 4 add the 2, you got the negative 2. The first add the third. And the negative 2, add the negative 2, I get the negative 4. And the 2 add the negative 2, I get the negative 2. Then if I add the first row to the second row to the new third row, that's exactly the same as the second row. So you got it? So what I'm telling you is the third row is really redundant. Now if you get the same, you subtract this new third row to the second row, what you get? 0, 0, 0. Once you get 0, 0, 0 on the third row, you know it's going to be a singular matrix. That's of course. And you know the rank is going to be at most 2. In this case, it is 2. Let me erase all those. So we only need 2 equations. We got a free variable we can use. You can select any 2 variables. Let's select the first one, negative u1 minus u2 plus 2u3 equals 0. Select the second one. Or you can use the Gauss-Jordan algorithm to solve it. I can at least divide by 2. I got this u1 negative 2 minus u2 plus u3 equals 0. Negative u1 minus 2u2 minus u3 equals 0. And if you add the first to the second, we get the negative 3u1 minus 3u2 equals 0. That means u1 equal u2. Now since the u equal negative u2, then if I let the u2, I can let it equal anything, equal 1, then the u1 equal negative 1. Or I can let the u2 equal negative 1, then the u1 equal 1. They are equally good. So what about the u3? You look at this equation 1, the u3 equals u2 plus 2u1. It's going to be negative 1 plus 2 is 1. Then your v, at least one of them, is 1, negative 1, and 1. If you afraid to make any mistake for the quick calculation, now you can multiply. Negative 4 times this. Negative 4 times 1 is negative 4. Negative 2 times negative 1 is positive 2. 2 times 1 is going to be 2, is 0. So this is good. You multiply this, negative 2 plus 4, negative 4 times negative 1 is 4, and then minus 2, again is 0. The last one, negative 2 times 1 is 2, minus negative 2 times negative 1 is plus 2, and then minus this times this is 4, again is 0. So you can check, you find that yes, this is the first eigenvector. Then you ask me, hey, why I want to choose this equal 1? Well, you can choose the equal t. That's what we did before. If you make this u2 equal t, and then u1 is going to be negative t, and then u3 is also going to be negative t, and you're going to put it together as a solution negative t, negative t. It's the same thing. They're on the same straight line. Take the t out. It's negative 1, 1, negative 1. You make a t equal negative 1. You got exactly the same thing. So what I'm saying is I really do not consider the magnitude much. All I need to get is the direction. If you recall the geometric meaning about the eigenvector, all you need is the imager stay in the same direction of the vector. So I selected the easy one, 1, negative 1, 1. We only got one of them so far.